Hello, good morning. So happy late New Year. So welcome again to this World River and Delta System Source to Sink webinar series. And today, this is the first webinar in this new year. So S2S21-01. So we invite Professor Chuck Nittrouer from University of Washington. He will talk about Amazon River derived sediment. So before I introduce Chuck, I would like to mention last year in 2020, we have successfully had 35 talks, and all those talks have also been very well archived and preserved over the YouTube channel. So if you missed any talk, or if you want to reuse any talk for your teaching in your classroom, for the research, for your research group discussion, so welcome, feel free to use it. The website is very simple. It's tinyurl.com/source2s talks. So you also can search over the YouTube or go to our website. So in this coming year, for this year, in 2021, we have also a bunch of very terrestrial, the fantastic talk are lined up already, as you can see all over. You will receive weekly email from me. And also, if you want to check more detailedly, you can go to this website, and maybe you already have it. So also next week, we will have two more talks. One is given by Shuye from Tongji University. He will talk about Yangtze River derived sediment. Other one is Michael Steckler from Columbia University. He will talk about Ganges Brahmaputra next Friday. So next Friday, we will have two more talks. So mark your calendar. And this is the talk for next Wednesday given by Shu Ye. So I will talk about a little bit more detail later. So Chuck, so this is from his CV. And he graduated from a PhD from University of Washington. And after that, he spent almost 9 years, I think, in North Carolina State University. Definitely, Chuck, you are the member of the Wolfpack. And after the NC State, he worked a couple years in Stony Brook, and now is a professor and a retired professor from University of Washington. But I want to show a little bit about Chuck of the research. I guess all the audience here, many of the audience know him well, but I want to see his research, the PhD research studied from the western coast here, Columbia River and Washington Shelf. And then he studied the AMSED with Dave DeMaster and many other colleagues as the Amazon River derived sediment on the shelf here. And then he shifted to earlier 1980s, many US colleagues with the China and the US collaboration of the Yangtze River mouth in East China Sea. And then he also worked on a little bit on the Ross Sea, and then go to the Spain, the Ebro River. And I remember he sent Steve Keel have a research cruise in the summer. And then he go to the New Jersey shelf, work on the continental shelf over there, and Nova Scotia over there. And then he working also the Yellow River derived, the Huanghe, the Yellow River derived sediment, the famous paper by Clark Alexander, DeMaster, and Chuck about the Shandong Peninsula, the mud wedge over there. Then he work on Antarctic Peninsula, and then go to here, North Carolina, Wilmington, the canyon and the shelf edge, and then shifted to Korea, South Korea, the tidal flat. And there's I saw the couple picture, Dave and Chuck and Oscar Clark dragging something over the mud, the flood mud. That's a beautiful picture. And also working on the Alaska Brickoba River, the southern Alaska, the river, the glacial derived sediment. And then go to Baltic Sea. I remember there's special issues about the budget, the methane, the biogenic gas sediment in the Baltic Sea. And then other very famous project is the Eel River and western coast of the Strata. We know Chuck is the leading scientist and for initiate of the Strata. And then also go to the Papua New Guinea, the Fly River, Gulf of Papua, study over there the source to sink margins program. And also, here in the Adriatic Sea, the Pearl River, the Ura Strata project, and also the Gulf of Lyon, the Rhine River sediment-derived sediment. And as you can see, go on, and last couple of years, he worked on the Mekong River sediment, the tidal river channel, and also jump back of the South America in the Chile about the the margin and the canyon system, the fluid system. And then I think most regions recently, he and his colleague and student working on the Myanmar in the Irrawaddy River derived sediment. I think there's also missed a couple, but overall, as you can see, what a career as a river, as a marine sedimentologist. He's very lucky and also such a good model for everybody in the audience, able to cover so diverse the global and different setting all the way from tropical to the high latitude glacial environment. So I think, I will give the floor to Chuck, and today he will mainly talk about the earlier work about the onset, and it's a little bit review, but I will point out there's many of other research. You should go to his website if you're interested of that kind of publication. So Chuck, so now you can share your screen.
Okay. Thank you, Paul, for those kind words. It's great to be here. You've had 35 terrific talks with more to come, and I'm glad to be one of those. I'm going to be talking today about the Amazon system with a focus on sediment transport and accumulation. We'll journey through the whole system, but I'm going to focus on the segments where you have mixed fluvial and marine processes operating in various combinations. This presentation is a summary of a paper that was published just last week, and the co-authors of that paper should be considered co-authors of this presentation. I encourage you to look there because there's more detail than I'll be able to present today, and also the references that I cite, you can get access to them in the reference section. Here's the description of the paper and its location online, and it was published in the Annual Review of Marine Science. If you have any trouble getting access, just send me an email message at this address and I'll be happy to send you a copy. So we're going to be talking about the Amazon system. It has a number of special characteristics. It's distinctly tropical with its mouth at the equator and its basin on both sides of the equator. It's extremely large by most metrics. It's the largest in the world. The dimensions, the size of the system, and the discharge of water, solutes, and sediments are the largest in the world today. It's also a very energetic system. Tremendous amounts of fluvial discharge. Most marine processes are at extreme levels. So the portion of the system where these fluvial and marine processes overlap, which will be the focus of my talk, is obviously also very energetic. It's a system which is surprisingly natural in state still today. It's had negligible amounts of channel dredging, artificial levees, water diversion, or ground fluid extraction. And it's relatively recently only that we have had deforestation and damming. It occurs on timescales of a few decades, not centuries and millennia, as we see for these processes in North America, Europe, and Asia. Consequently, the system and the processes that we look at have great geological significance. The land and ocean processes that are recorded in the stratigraphy are high fidelity. They actually represent something that with geological relevance, not something that's been intensely manipulated by humans. The large scale of the system means that the active processes have global relevance, and we'll see that the length scales in particular allow, and the magnitude scales allow us to see processes clearly displayed. The goal of my presentation is going to be to summarize the sedimentological linkages from source to sink with emphasis on part of the system. We're going to be reviewing direct observations that have been made over the past half century. We'll be looking at a serial chain of sedimentary environments as shown here in this diagram. The approach will be a source to sink approach, which means that in addition to looking at processes within the discrete segments of the system, we'll also be interested in the linkages between the segments of the system. And as I said, we're the continuum of the segments that have fluvial and marine processes will be focused on. So this is the outline of the talk. There'll be an introduction at the beginning, a summary at the end. We'll spend a little bit of time talking about the purely fluvial part of the system and the purely marine part of the system. But as just mentioned, we're going to be focusing on these segments where we have various combinations of fluvial and marine processes overlapping each other. Just a couple words about the source to sink approach. Myself and many other people have spent decades focused on discrete segments of the system and understanding the operation of processes in these discrete segments. One of the tenets of source to sink is that we also need to be interested in the transfer between exchanges between the different segments. It's thought that the signals that propagate these can be amount of sediment, size of sediment, whatever property you're interested in. As you move from the source to the deep sink part of the system, it's thought that not only, as I said, not only do you need to understand what's happening within them, but also you need to understand the exchange between the systems. Among the factors that are affected are the speed, the direction, and the quantity of sediment transfer through the system. Specific factors that become important are the timing of the transfer, the coupling of active processes, and the amount and type of sediment. And I'm going to come back at the end and explicitly address these factors as they relate to the Amazon system and the lessons that we'll learn from the presentation that I give. This is the terrestrial part of the Amazon system. It extends from the Andes in the west to the Atlantic Ocean in the east. Because it has such a large drainage basin, it has many tributaries. In fact, those of you that count the order of tributaries, the Amazon itself is actually a 12th order tributary of all these other smaller systems that feed into it. For example, here's the Beni River that drains, receives the input from mountainous rivers in the Andes. It's a tributary to the Madeira, and the Madeira is a tributary to the Amazon itself. The tributaries are often distinguished based on the headwaters and the characteristics of those headwaters impart. Those that have headwaters in tropical rainforests often are described as black water because they have much dissolved organic matter. A good example here is the Rio Negro. Those with headwaters in the Amazon are often described as white water, although it's really more of a milky chocolate because of great amounts of suspended sediment. Good examples are the Solimois and the Madeira tributaries. In some cases, the tributaries have neither large amounts of dissolved organic matter or suspended sediment. And these often come off of the crystalline shield areas in the lower part of the system. And good examples are the Tapajós and the Xingu, which enter the tidal river part of the system. Tides extend 800 kilometers upriver to Óbidos. This is now the beginning of our discussion of the system. We're going to start up in the purely fluvial part of the system. This shows the elevation changes as you move out of the Andes down into the Amazon plain along the transect shown here by the dark line. The great relief in the Andes leads to the production, the weathering, and erosion of most of the sediment that's delivered by mountainous streams out of the Andes down to the plains. Turns out that about in excess of 90% of Amazon sediment is produced in the Andes. The absolute amount is somewhere between 2,000 and 3,000 million tons per year. However, only about half of this reaches the beginning of tides at Óbidos. And a big reason for this is the very gentle gradient for the Amazon plain. In the last 3,000 kilometers, it only drops something less than 100 meters. That allows for entrapment. The beginning of entrapment is within the Shoreline Basin at the base of the Andes. Eduardo did a great job talking about sedimentation in this area, and I encourage you to go to his talk number 9. I will just say a few words about the Beni, which I mentioned earlier, one of the tributaries to the Madeira. We can look at quantitatively at the entrapment of sediment on its floodplain, right at the levee of the river channel. We can see that accumulation rates are in excess of 5 centimeters per year. Even as much as 3 kilometers away from the river channel, we still have accumulation rates in excess of 1 centimeter per year. The entrapment of sediment through the rest of the fluvial part of the system down to Óbidos continues, although the mechanisms for the entrapment do have some differences as you move along the system from the Shoreline Basin to the lower parts of the system. This figure here is from work by Tom Dunn and his colleagues. And what we're looking at is various segments of the fluvial part of the system down to Óbidos. The width of the segment is proportional to the amount of sediment that's being fluxed through that segment. On the upper side, we're looking at the fluxes of input from the various tributaries. The Madeira is the biggest tributary of sediment to the Amazon system. And what we're looking at down below here is the entrapment that they calculated for the various segments. And you can see some of the lower areas here toward Óbidos, we get great entrapment of sediment. The processes operating there are floodplain lakes dominating both sides of the Amazon mainstem. These lakes modulate Amazon flow. During rising water, the lakes tend to store water, and then during falling water, they tend to release it. The input of sediment into the floodplain lakes during high water, gets in through diffuse overbank flow, and the draining of the lakes is both as overbank at the beginning, and then through the draining process, it goes through crevasses. I'm going to mention this a couple times, but be aware that the levees of the Amazon are almost entirely natural levees, and the crevasses similarly are open, continue to be maintained naturally and in an open condition. When the water leaves the floodplain lakes, what remains in the floodplain is thought to be about 40% of the sediment that's carried in with this, the turbid Amazon water. For the stretch from the Purus Arch down to Óbidos, this lowermost segment, something in excess of 1 million tons per year, 100 million tons per year is thought to be trapped within that segment. Obviously, water and sediment does get to Óbidos. I'll just repeat again, this is 800 kilometers upriver from the ocean, but this is the beginning of tides. And so it's the lowermost gauging station. We can see 40 years of hydrographic records for the Amazon. The peak discharge is during May and June, and the minimum discharge is typically during October and November. This is different than the sediment hydrograph. The peak sediment discharge, as we see here, is earlier, distinctly earlier in February and March. This is important because it means that the greatest amount of sediment fluxing down the river does so before the water level has reached the levee crest and started to significantly flood the floodplains. The reason for the timing of the sediment discharge, it's associated with the seasonal migration of the intertropical convergence zone that moves back and forth through the Amazon basin over the year, and the location and the yields of the various tributary basins within the Amazon system, and of course the hysteresis of storage and sediment release. The estimates of the amount of sediment that pass Óbidos, according to Bob Mead, are on the order of about 1,200 million tons or 1.2 billion tons per year. And this sediment is largely silt and clay, about 90% mud that's finer than 63 microns. Okay, so now we've moved down to the tidal river. This is the segment of the system where we have tidal modulation, but there is no salinity. Fluvial geomorphologists have done a great job studying the fluvial part of the system, part of which I just barely touched on previously. But they stop when they get to the beginning of tides. And this is where we have the lowermost gauging station on most rivers and the Amazon as well. This is where, this is Óbidos. Marine scientists, oceanographers do a wonderful job investigating the more distal part of the system, but they stop typically when they run out of salinity. So the tidal river in general is a fairly understudied part of most big river systems. And it should also be mentioned that for most big rivers, the tidal river is intensely manipulated by humans. So we're really lucky to have the Amazon system, 800 kilometers, where we can look at the effectively natural processes that operate within a tidal river. Of great importance to the tidal river is the fluctuation of water level that delivers sediment to and from the floodplain areas and to other environments along the system. What we're looking at here are 3 panels nearly at low tide, low seasonal flow in December, rising water in March, and high water in June. And then within each of the panels, we're looking at a diurnal fluctuation in water level. And what we see is that the primary mechanism for water level fluctuation for Óbidos, OBI here, is the seasonal fluctuation in the water discharge in the river. However, if you move down toward the ocean part of the system, what we see is that the primary fluctuation in water level is driven by the macrotidal conditions that are observed at the mouth of the Amazon. This part of the system has relevance because if you look at sediment budgets, as we said, from Bob Mead's estimate, something around 1,200 million tons per year past Óbidos. In the ocean, we can only account for something on the order of about 800 million tons per year. That leaves about 1/3 of the sediment that possibly accumulates within the tidal river. However, there are major caveats on this. Among those, there are big confidence limits on the numbers stated up here. In addition, the techniques that are used throughout the system vary in the means by which we calculate, and especially important is the time scale over which they integrate the measurements of transport and accumulation. So I would be leery about fully accepting this 1/3 number. However, it's very likely that the amount of sediment that is trapped within the Amazon tidal river is measured on the order of hundreds of millions of tons, and therefore understanding the processes that trap that sediment is a worthwhile endeavor. A big reason for the entrapment is because of accommodation space that was created due to incision during the last low stand in sea level. This is measured on the order of tens of meters, and it extends for over 200 kilometers up the river in both the mainstem and the tributaries of the river. Now, Since the low stand, there's been some infilling, especially of the main stem of the river, but also some of this accommodation space remains. It especially remains within the tributaries that enter the tidal river, the Tapajós and the Xingu. I'm showing here the Tapajós, but it's representative of the Xingu as well. The mouths of the river are described as rias. These are quiescent lake-like environments. They have widths on the order of tens of kilometers. They extend upstream over 100 kilometers till you get to the more typical fluvial channels part of the system. And they, as we said, they still have this incised depth with depths that extend down as much as 50 meters. The small amount of sediment that enters tends to be trapped largely in bayhead deltas at the head of the rias. And we'll see that there is Amazon sediment that's accumulating within the mouths of the rias. This cartoon is for the Tapajós in particular, but again, it reflects processes for the Xingu as well. This is the confluence area of the clear water for the Tapajós and Xingu, where it meets the milk chocolate waters, the white waters of the Amazon. And there are a couple mechanisms, actually several mechanisms that deliver sediment from the Amazon, the turbid water, into the quiescent mouths of these rias. One of those are barotropic flows due to elevation differences that occur seasonally because of the discharge level of the Amazon. But also we have the semi-diurnal fluctuation of tides that also bring the turbid water into the ria. There are also density-driven underflows. These are due to the fact that Amazon water is typically colder and it has significantly more suspended sediment that allow bottom flows to bring sediment in. Another interesting process that's observed distinctly at the mouth of the Tapajós is that among the natural crevasses and levees, which I've already said, those crevasses with the proper elevation differences allow the turbid water from the Amazon to flow in, and they've created some very interesting bird foot deltas within the mouth of the Tapajós. And these features occur further down the tidal river, where you have crevasses that enter into the floodplain in that part of the system. I wanted to mention that the integrated amount of Amazon sediment that's calculated to accumulate in the mouths of the Tapajós and the Xingu combined is on the order of about 20 million tons per year. Now, this number is small relative to 1,200 million tons that we mentioned passed by Óbidos. However, it's important to recognize that the Tapajós and the Xingu consequently are not sources of sediment. I mean, yeah, not sources, but are sinks of sediment. The area, the surface area where you have the greatest potential for trapping sediment within the tidal river is in the floodplains on either side of the main stem of the Amazon in the tidal river between Óbidos and the ocean. As we've said, the fluvial processes tend to decrease in significance as we move from Óbidos toward the ocean, and the marine processes, in particular, the tidal process, tends to increase in significance as we move to the macrotidal conditions at the mouth. This overlap of processes cause differences in the morphology of the floodplain and also in the character of sedimentation on the floodplain between the upper tidal river, the central tidal river, and the lower tidal river. And we're going to spend some time now looking at each of these. In the upper tidal river, we have substantial levee heights. They are 7 to 10 meters in elevation, which limits the exchange, the delivery of water from the main stem to the floodplain. As demonstrated here, this is a photo from one of the floodplain lakes in the upper part of the river, of the tidal river, very similar to the floodplain lakes on the other side of Óbidos, the lower part of the fluvial, purely fluvial system. And you can see the turbid water within the floodplain lake this is the exact same location during low water. And so during much of the hydrograph of the river, we're not able to supply new turbid water to the floodplain. Consequently, the accumulation rates compared to the rest of the tidal river floodplain are moderate. They're on the order of a centimeter per year, and we are left with still much accommodation space on that part of the floodplain. When we move to the central tidal the central tidal river, you see that the levees are much more muted in character. This is largely because we have tidal ranges of 1 to 2 meters in the central part of the river, tidal river, and we have flood, ebb. So we have currents moving across the levees 4 times a day. The transport mechanism that's moving the Amazon water onto the floodplain now is an effective transport, which is a more effective means of moving suspended sediment far into the floodplain. Accumulation rates are significantly greater than for the upper part, and we see accumulation rates in excess of a centimeter per year, and consequently also a significant portion of the accommodation space has been filled, although some still remains. When we go to the lower part of the tidal river, there are no levees. The floodplain is built up to sea level. That's because the tidal processes have been successful doing their job and infilling the floodplain. Today, what we have are basically freshwater tidal flats. The flux of water and suspended sediment are through tidal channels, very similar to what we see for marine tidal flats. Consequently, since we've built up to sea level, accumulation rates are limited. They're only a couple millimeters per year, and they're controlled by the accommodation space that's being created due to sea level rise. And before I leave this panel, I do want to highlight the fact that the central part of the tidal river is the portion that it's the sweet spot in the transition from fluvial and marine processes as we go down the river. And consequently, it's the area where we have the most effective sediment entrapment. The mainstem is extremely dynamic, as you could imagine, both for water and for sediment. As we approach the Amazon, you not only have the tremendous discharge of water through the system, but you also have the macrotidal conditions at the mouth that can exceed 5 meters during spring tides. This actually causes reversal of flow as far as 300 kilometers upriver. The mighty Amazon reverses flow. And we can see this if we look at the data over here on the right. These are ADCP observations across, in this case, the north channel of the Amazon near the city of Macapá. And you can see here on the right the speeds. And these measurements were made, shown here over a semi-diurnal period. The tides of the Amazon are actually very symmetrical, so you can understand the tidal fluctuations by just a semi-diurnal. You don't need a full diurnal period of observation. Over here on the left, what we're looking at, positive values of discharge mean the flow is downstream, and negative values means it's upstream. So what we see is that we have downstream flow during ebb tides, and we have upstream flow during flood tides, not surprisingly. But the transport actually reverses between the ebb tide period and the upstream period. And as we said, this reversal extends as much as 300 kilometers upriver. If we now go to the central part of the tidal river system to near the village of Almarain here, we see that the discharge still very semi-diurnally, greater during ebb and weaker during flood. But now what we have is a stuttered flow with the greater velocities during the ebb tide and weaker velocities, but during the flood tide, but during both periods, it's downstream. And I want to also point out the velocities we're dealing with here. In both cases, in both areas, we have velocities in excess of 200 centimeters per second, and the associated bed stresses are severe, and they have an impact on the bed sediment, which we'll be looking at in just a second. But first, I just want to emphasize everything we're talking about here is freshwater. We don't see salt until we get out into the Atlantic Ocean. So the great shear stresses and velocities mean that the bed sediment is sand that's deformed into sand waves as much as 10 meters high. As you approach the channel flanks, we have interbedded sands and muds, and especially as we get down to the lower part of the system, under the freshwater tidal flats, the sediment is almost entirely mud. Just a mention about mineralogy. We start in the Andes with exotic mineralogies, but by the time we get to the sediment that's supplied to the ocean, most of the sand, well, the weathering processes cause most of the sand to be quartz and most of the mud to be kaolinite. So now we've reached the marine part of the system. Here's the mouth of the river, just north of Marajó Island. And I want to point out that the mouth of the Amazon is neither a classic estuary nor a classic delta. The definition of estuary is where freshwater meets and mixes in a semi-enclosed environment, but all the meeting and mixing of Amazon water with Atlantic Ocean water occurs out on the continental shelf without spatial constraint. And similarly, at the mouth of the river, we don't have a subaerial feature protruding from the shoreline as expected for a classic delta. However, as mentioned, we have estuarine processes of great significance, but they occur out on the shelf. And also we have a distinct subaqueous delta associated with the Amazon, which is also out on the shelf, creating a clinoform feature that we'll be talking about. And also the sediment that escapes leads to shoreline accretion, both south of the river mouth, where we have a barrier shoreline, and north of the river mouth, a stretch of erosional, but then a very long stretch of muddy shoreline accretion north of the river mouth. So we're going to focus now on the continental shelf and the shoreline portions of the system. This is the bathymetry near the mouth of the Amazon. We can see that there's a relatively gentle gradient out to the 40-meter isobath. This is the top set portion of the shelf clinoform. Between the 40 and 60-meter isobath, we have the isobaths close together, which indicates that we have a relatively steep surface. This is the foreset region of the shelf clinoform. And then at the base, we have the thin bottom set sediments. Most of the modern sediments from the Amazon are mud, and they do not reach the shelf break. Modern Amazon sediment does not reach the shelf break. There's a fairly wide swath of relic transgressive sand that's found along the shelf in places greater than 100 kilometers in width, and especially in the southern part of the system. Across the mouth of the river, there's this transverse shoal that's shown where water depths are less than 10 meters. This is the landwardmost extent of the salt water that is heading toward the mouth of the river. Just north of the river mouth, near Cabo Norte, we have a shore perpendicular shoal that extends seaward, and it divides the proximal shelf area into two but similar segments, one right at the mouth and one a bit farther north. As I said, there's the barrier coastline to the south, where we'll see that there are multiple sandy barrier islands. Then to the north there, we're going to see an erosional part of the coast, and then a very long accretionary part of the shoreline as we go northward. Shelf break is at about 100 meters depth. It's incised by the Amazon Canyon, which also incises the continental slope. And then at the base, we have the Amazon fan that builds out on the continental rise extending to the Demerara abyssal plain. Among the processes that affect sedimentation on the shelf are the seasonal changes in the trade winds. They blow strongly on shore during the first half of the year, which also increases the surface gravity waves. They're more energetic during that period. During the second half of the year, the winds blow parallel and more weakly, parallel to the shoreline and more weakly. These affect the pathways of the Amazon water and suspended sediment on the shelf. The Amazon plume primarily moves in a northwestward direction, driven by the North Brazil current, which is a geostrophic western boundary current of ocean scale. It accelerates in velocity during the period when the flows are shore parallel toward the northwest, and consequently the plume of Amazon sediment also accelerates during that period. However, during the period when the winds blow onshore, the wind stresses tend to slow the North Brazil current, and they also cause the plume to bulge in a southward direction. And this is probably when most of the sediment nourishes the shoreline to the south. When we look at the area near the mouth of the river, what we see is that not only is the large discharge of fresh water significant, not only is the energetic North Brazil current important, as well as the continuous trade winds, but we also see macrotidal conditions still have a significant effect on sedimentation. During spring tidal conditions, the more energetic currents cause resuspension of suspended sediment high into the water column. And they tend to concentrate, during this period, we tend to concentrate the small amount of sand that reaches the ocean in the Amazon system at the seabed. During neap tides, the more quiescent conditions allow the suspended sediment to collapse toward the seabed. And we have very high concentrations of suspended sediment. However, I want to point out that during both periods, we typically have concentrations near the bed that exceed 10 grams per liter. This is critical. It makes them fluid muds and gives the water with these concentrations a density that's sufficiently greater than the ambient seawater, such that the fluid muds can move down a sloping surface under their own weight. And before I leave this, I did want to point out from a stratigraphic standpoint, this is an X-radiograph positive from a core near the mouth of the river. Because of the changing conditions at the bed, we typically form what are known as tidalites, the inner bedding of sandy deposits and muddy deposits. And in fact, if you look in more detail within either of these, you can see finer laminations. So we have inner bedding on fortnightly timescale, but we have this inner lamination that probably reflects semi-diurnal fluctuations in tidal conditions. As we move north of the river mouth, we see that most of the sand has been left behind near the mouth, and the system is almost entirely dominated by mud. However, you still have estuarine processes that are active there. You have low salinity water that moves in a seaward direction, and higher salinity water, ocean water, that's moving in near the in the lower part of the water column. Right near the seabed, we'll see that there is an impact that comes from the fluid muds that are found on this part of the shelf. However, first I'd like to talk about the upper parts of the water column. This is a satellite photo of real colors. And we're looking at what we see here is the milk chocolate color of the Amazon water that moves out and is carried northward with the Amazon plume. These waters typically will be in excess of 10 milligrams per liter, which makes it difficult for sunlight to penetrate sufficiently for any sort of primary productivity. However, there is a great deal of dissolved nutrient, phosphorus and nitrogen, that's also discharged by the Amazon. And this is able, once we get beyond this controlling level of about 10 milligrams per liter, when we drop below that, then diatoms, algae, phytoplankton are able to bloom, and we see the creation of this green water farther seaward. This is something that Dave DeMaster discussed in his presentation earlier, and I encourage you to look at what he showed. It's important to recognize that this productivity of or production of green carbon in this part of the system ultimately settles through the water column. And as it does so, it hits the landward flowing deeper waters. And so it is brought back landward and is supplied to much of the clinoform surface along with the terrestrial carbon that's coming down the system. So you have both labile and more refractory carbon being added in fairly large concentrations to the clinoform also. Once we get beyond the turbid water and the green water, the brown water and green water, and we get farther seaward, we're into the oligotrophic blue waters of the tropical Atlantic. I did want to talk about the significance of sedimentation in this region, and in particular the impacts of fluid muds. I suspect that Gail Konecki will touch on this in her presentation later this year. A really important part of the season is the first half of the year. This is when the winds and waves have intensified and have resuspended or just maintained sediment in suspension. It's also the period when you have the greatest discharge of new sediment from the river. Together, these muddy materials tend to enhance the fluid muds. They expand both in a seaward and landward direction. The landward direction will nourish the shorelines, which I'll talk about in a little while. First, we're going to talk about the seaward expansion and its effect, in particular, moving sediment from the topset to the rapidly accumulating portions of the foreset. This is a figure that Steve showed earlier in his presentation. It's a lead-210 profile, lead-210 activity across the top, and it's from a sediment core. So here's depth and core that we're looking at here. It's a distinctly non-steady state profile. Lead-210 profiles tend to be log linear, decreasing with depth. What we're looking at here, however, are fluctuating activities. We have these pulses with thicknesses of tens of centimeters that represent the movement of fluid mud from the topset to the seaward part of the clinoform to the foreset region. And then between these pulses of fluid mud getting to the foreset, we have the higher activity, which represents particles that are settling from the plume through the water column, and especially scavenging dissolved lead-210 from the ocean water that's being brought landward. And so you get this fluctuation of both the pulses of fluid mud and also periods of more pelagic sedimentation reaching the seabed. Together, they cause accumulation rates in excess of 10 centimeters per year on the foreset region, which is this steeply dipping part of the system. Accumulation rates on the topset are less. They're in single digits of centimeters per year. And as we move out to the bottom set, these thin deposits here, accumulation rates are millimeters per year. This is a very instructive figure. It's a seismic profile across the Amazon system, Amazon clinoform. What we're looking at is the history of sedimentation in the last 12, 15,000 years. This is the coastal plain surface, the old land surface during the last low stand of sea level, which you can see is in size by channels when it was a land surface. It's been buried by a transgressive surface that formed as sea level rose. And then that surface subsequently has been buried by the modern clinoform that's prograding upward and outward on the shelf. And this probably began to reach and build out onto the shelf about 6,000 years ago when the rate of sea level rise slowed significantly. We see that our ability to look at structure within the seabed is masked as we move landward. This is due to methane gas. This Methane is due to is produced by methanogenesis due to the decomposition, the diagenetic processes associated with the marine carbon, as well as some of the terrestrial carbon that we were talking about earlier. This diagenetic process is very complex, and Bob talked about it in his talk number 21, and I encourage you to listen to that talk for more of the details. Before I leave this figure, though, there are several points I want to make. One, the biggest sink for Amazon sediment in the system is the clinoform on the shelf. Probably on the order of about half of the sediment passing Óbidos is accumulating within the clinoform on the shelf. So it's an important part, especially in terms of accumulation within the source sink system. I wanted to reiterate what I had said before, that modern sediment does not reach the shelf break, both in the bed, but also in the water column. The sediment peters out before you get to the shelf break, and consequently, we're left with relic sands on the outer shelf. Recently, a number of studies have investigated mesophotic reefs that are present on the outer shelf off the mouth of the Amazon today, which are actually creating carbonate sediments. And then next, I wanted to address what's implicit from this figure, but I want to do it explicitly, and that is the natural changes in sedimentation that can occur in this environment. So here we're looking at low stand conditions, this surface here. Then we have transgressive conditions, high levels of sea level. So through the timescales of thousands of years, we have a natural change in sedimentation. This is observed not only on timescales of thousands of years, but it can be observed on timescales of centuries and even decades. Here we're looking at a snippet of a seismic profile from the topset region near the mouth of the Amazon. The scales here are, the vertical scales are meters, not tens of meters as shown on this upper figure. And we're looking at very distinct changes in sedimentation that have occurred naturally. This is transparent mud that's actively accumulating and has created a layer that's about 7 meters thick. There's a very distinct unconformity surface here, a period of erosion. And then before that, we see that sedimentation was creating these dipping reflectors, which are significantly different than the sedimentation regime that we see today. So again, on shorter timescales of centuries. Oh, and I should mention that the carbon-14 dates for this region that Chris Summerfield made indicate that we're looking at something in the order of about 1,000 to 2,000 years of accumulation here. So on shorter timescales, we also see naturally changes in sedimentation. So this is a very dynamic system. Now we're moving from the shelf to the shoreline, and we're going to start with the part of the shoreline south of the river mouth. Here's the mouth, Marysville Island. This area right here is Pará estuary. I should have mentioned that a small fraction of Amazon sediment, actually just a few % of water and sediment, actually moves southward behind Marysville Island and out the Pará estuary. This is the barrier shoreline south of the river mouth. We're going to look at a transect here near the city of Bragança. This is the transect out to the modern barrier island system offshore. And this is the transect. And what we see are multiple stages of barrier growth. There's an old barrier island system with mud infilling it behind, a second sandy barrier island with mud that's accumulated behind it. And then there's the modern sandy barrier island, and there's active muddy accumulation behind it. That muddy accumulation does so as mudflats and in very extensive mangrove forest, as you can see here. And what's important to recognize is that the amount of mud, the mass of mud that can be calculated to be accumulating today is significantly greater than can be explained by local supply by orders of magnitude. And it's almost certain that the source of that mud is from the Amazon, although it, a good direction for future research would be to directly document the transport processes toward the south. But they probably occur during the period of year when the plume bulges in the southward direction. North of the river mouth, the shoreline is significantly different. We actually go from macrotidal conditions to hypertidal conditions. Tidal ranges in excess of 10 meters. We get tidal bores, known locally as the Pororoco in this area. The reason for the intensified tides is the funnel shape that's created by the shoreline and the shore perpendicular shoal here by Cabo Norte. Those increased tidal currents cause erosion of the coastline. The jungle vegetation is falling into the ocean, but it's important to recognize, again, carbon-14 dating of these sediments indicate that they were accumulating just 1,000 to 2,000 years ago. So again, as with the shelf, there are natural processes that have led to fluctuations in sedimentation on the shoreline as well as in the shelf part of the system. As you move northward away from Cabo Norte toward Cabo Cassiopore and Cabo Orange, what you see is that the tidal range progressively decreases to where it's just a couple meters in range when you get up to these northern areas. The nature of shoreline sedimentation changes dramatically. Rather than being erosive, it's accumulating. The mechanism of accumulation is as northward prograding mud capes or mud banks. You have, again, mud flats, which are being colonized by very densely populated mangrove forest. And together, these environments are moving and retreating in a northward direction on both Cabo Cassiopore and Cabo Orange. Calculations of sediment transport past this point are thought to be on the order of about 150 million tons per year. We'll look at the accumulation farther north. But first, I wanted to step back and look at the sedimentation that we see from a stratigraphic standpoint. And presently, during the high stand and sea level, we have a distinctly two-stage mechanism of strata formation. We have the bulk of the sediment accumulating and the stratigraphy forming as the shelf clinoform. And then it's being built out over its top by the shoreline processes that I've just described. Together, these have the potential to accumulate probably in the order of 30 or 40 meters of sediment. However, if you look deeper within the seabed at the preserved strata, now this is another deeper penetrating seismic profile, we see very distinct erosional surfaces, unconformities. They are cut by channels, like the channels that I showed earlier. And the thicknesses of the preserved packages are somewhat less. They're on the order of probably about 20 meters or so, which suggests that during low stands in sea level, that erosion does tend to decapitate some of the package of sediment that's created during high stand conditions. Okay, now we've moved from the proximal part of the system to the distal part of the system. And although the Amazon sediment and Amazon water are still recognizable, the processes which are driving their transport and accumulation are purely marine processes. The impact of the fluvial discharge has diminished. But we do see that Amazon sediment nourishes the seabed for over 1,000 kilometers northward up to the Orinoco River. It does so as a continuing series of these mud capes or mud banks extending in the northward direction. Edward did a great job describing these in his presentation. I encourage you to look at his talk number 13. The Amazon sediment that nourishes up to the Orinoco Delta continues, although it's significantly diluted by sediment from the Orinoco, but mineralogically, we can still recognize Amazon sediment into the Caribbean Sea. Now, this is what we observed during the present high stand in sea level, and it's very likely typical of what occurs during high stand conditions, but during low stand conditions, the processes in the distal part of the system is substantially different. During low stands, the Amazon delivers its large amount of sediment to the head of the Amazon Canyon, which flows down the Amazon continental slope. And we see very distinct impacts from debris flows on the slope. We also see well-developed evidence of turbidity currents in the form of meandering channels that have very recognizable levee complexes that are created. These channels go through avulsions. They move back and forth across the fan. They bury at pre-existing channels. And they have led to a very interesting history of turbidity current supply that, together with the debris flows, have created the Amazon fan that's building out onto the Amazon continental rise. And some of those turbidity currents extend, as I said, into the Demerara abyssal plain and lap up against the flank of the Mid-Atlantic Ridge. So I've reached the end of my presentation. We're now to the summary stage. As promised, I just wanted to touch on the relevance of some aspects of the source to sink concepts as they relate directly to the Amazon. I'm just giving 3 examples here, starting first with the importance of the timing of transfer between segments of the system. As we mentioned, the peak sediment delivery within the river occurs when the water level is below the levee crest. Consequently, large amounts of sediment are able to reach the ocean, and they do so during a period when the ocean is in energetic conditions. The sediment that's already been there has been resuspended and maintained in suspension, and now we have new suspended sediment that's added. And together, this material is very important for being transported during this period to both the foreset and the shoreline, leading to the progradation of the clinoform and also the progradation of the shoreline. An example of another significant source to sink concept, the coupling of processes. An example here that I'll give is the overlap in the transition of fluvial and tidal processes that cause the central part of the tidal river floodplain to be a very effective sediment trap today. And then finally, the amount and type of sediment, the progressive sorting that occurs throughout the Amazon source to sink system delivers only the finest fraction of sediment to the shelf, which allows fluid mud to dominate sediment transport processes there. Okay, now moving into the future, the processes that I've described will not, almost certainly will not be the processes extending into tomorrow. There are going to be changes both on an indirect and a direct level. The indirect perturbations are going to be on large global scales, such as changes that will affect the amount and timing of precipitation within the drainage basin, the acceleration in the rate of sea level rise. Already, higher flood amplitudes have been observed and more floodplain retention has been documented. The acceleration in sea level rise is going to create more accommodation space, both along the shoreline, but also extending for hundreds of kilometers upriver. So just reflect on this. If possibly a third of the Amazon sediment is now trapped within the tidal river, what happens if we triple the rate of sea level rise, which is entirely possible, creating new accommodation space, especially in the lower part of the tidal river system, which is very effective in trapping sediment. And then there are the direct human perturbations, which are going to dominate over the natural perturbations. And so the changes in sedimentation in the system, other than they'll no longer be driven by natural processes, but by human-induced processes, However, I do want to mention that it's very unlikely that channel dredging, artificial levees, water diversion, or ground fluid extraction will increase into the future. So we can focus on two very important human impacts, deforestation and damming, which have been occurring over the past few decades. Deforestation will have an impact on supplying more sediment to the system. However, the damming will not only trap this new sediment, but also much of the naturally supplied sediment. And it's pretty well guaranteed that both the shoreline and the clinoform will become undernourished relative to present conditions, although the full impacts are not known. And now is the time to document, understand, and mitigate. And I encourage Brazilian scientists, European, North American scientists to augment any work underway or to start new work to undertake this type of research for the Amazon system. It's a great opportunity to understand how a natural source sink system operates before it changes dramatically. And so just in closing, I want to say thank you. The insights that I've described have been obtained through collaborative studies over more than 4 decades. I want to point out that there's a very rich history of interdisciplinary studies. There have been many people studying the hydrodynamics of the river and the ocean. There have been geochemists also looking at the river and the ocean, as Bob and Dave's studies demonstrate. And there are biologists working in terrestrial and marine environments. Much of the research I've described was done while working side by side by these other scientists. And their work not only helped us collect the data, but also their studies help constrain many of our interpretations. I want to thank all the scientists for their extensive efforts that have come from dozens and dozens of scientists, technicians, and students who've helped in the field, on ships, in laboratories, and with publications. To all of these friends, we express our sincere appreciation. Funding for Brazilian scientists largely came from CAPES, CMPK, Petrobras, and from the US side from NSF and ONR. And we express our appreciation to these funding agencies for supporting the research. And I express my appreciation to you for listening. Thank you.
Thank you, Chuck, for this very comprehensive but fantastic overview review of the Amazon River system, all the way from the source to the sink, from the mountain, from the river, the floodplain, to the estuary, to the shelf, and to all the way the long shores and transport. So to the audience, if you have any question, you can type your question in the chat, or you can raise your hand. I will unmute yourself. And okay, I saw one person, Tianjian. Yeah, okay, let me ask unmute. Okay, can you unmute yourself? Go ahead, Tianjin. Okay, can you unmute yourself? Anybody else? Just go ahead, Bob.
Yeah, Chuck, you said that specifically that only the finest fraction of the supply reached the shelf, and but I remember when we did a time series station off the mouth on the shelf, that there were periods of time when sands were deposited and removed during the time series sampling, and also that you in your own maps show a corridor of sandy sediment extending across the shelf from the mouth to the deeper portion. So there must be, I would think there must be periods where sand is introduced, and I'm wondering what those might be. Is that high flow periods or not? So I'm just asking you, is it really true that no sand?
So just there was a figure that I showed at the mouth of the Amazon, the changing between neap tides and spring tides. When I highlighted that the bed tends to get sandy during the period of the spring tides, and that's what leads to the interbedding of the sandy and muddy deposits at that area. However, there's no doubt that the preponderance of mass of sediment is muddy sediment, and the amount of sand that does get there, clearly the deeper parts of the channels are the sandiest parts of the channel. So when that sediment, there isn't much difference between peak flow and low flow of the Amazon. So probably it's going to be when the discharge of the river is superimposed on ebb tide currents that some of the sand can get over the transverse bar at the mouth. And it gets there. I mean, the interbedding of sand and mud right at the mouth is recognizable. Probably some of the seismic profiles that show distinct dipping strata of different character. That's probably a concentration of sand due to periods of erosion. So there is sand that gets there. As you go down the system, though, there is less and less of it. And certainly then as you get to the marine system, as you move north, Cabo Norte, which itself we think is probably sandy, but we don't really know why or if it is. But when you get to the northern part of the proximal shelf, that is almost all mud.
Mhm.
The place you really see any sand up there is at some of the small coastal plain rivers right at their mouths. But yeah, there is sand, and that sand is where it's located is right near the mouth of the river. It doesn't get far seaward of that, and it doesn't get far along shore toward the northwest.
Okay, thanks.
Okay, great. Who's next? Dave.
So, Jack, can I have a question?
Yeah.
So, yeah.
Go ahead.
Yeah. It's a very impressive talk and very comprehensive. Thanks. My question is, you mentioned probably during the sea level change, there are strong erosion probably happen in the shelf, on the shelf, right? I wonder the erosion happened during the sea level rise or sea level fall. I mean, miss your talk, yeah.
Well, certainly as the shoreline migrates in a seaward direction during falling water, that's going to have an impact on the clinoform that's been produced during the high stand. But then you also have thousands of years when that re-exposed surface is available for erosion processes when it's a land surface. So yeah, during falling water as the shoreline passes by a location, but then for the thousands of years when it's sitting above sea level, you probably have erosion processes operating. Yeah, and then again, with rising sea level, it appears as though probably right at that interface between the pre-existing land surface and the shoreline as it moves by, there might be a little bit more erosion, but it seems as though it leaves behind a transgressive deposit pretty ubiquitously observed. I think a lot of the erosion, my guess is that much of it occurs during the period of time when sea level's low, and that previously formed clinoform is above sea level.
Okay. You also mentioned in the present day, probably the modern fine sediment cannot reach the continental slope, right?
Yeah, so both clearly in the bed, modern muds do not go to the shelf break. And also the work that's been done in the water column, the concentrations are extremely low, almost negligible by the time you get out to the shelf break.
Yeah, I mean, probably in the East China Sea, also we have very wide, relic sediment.
Even wider, yeah.
Yeah, sandy sediment. Yeah, but
this shelf is something in excess of 300 kilometers wide, and then East China Sea, you're looking at 500 kilometers. away.
Yeah. I mean, some scientists suggest even a fine-grained particle, maybe not much, but it still can, reach
Okay, I mean,
our path.
but you're in the rounding error of our calculations. Yes, it's possible that a particle escapes out to the outer shelf and maybe makes it to the continental slope. But in terms of the greater story, there's very little sediment that gets out there today.
Okay, that's great.
And that's not uncommon on many continental shelves. Off the Columbia River, there are many places where the outer shelf is relatively sandy, and it represents an old transgressive surface. And unless you have a submarine canyon that incises deeply into the dispersal system, you're not going to get the sediment out to the continental slope today. And then even more of continental shelves, if you have estuaries active like the east coast of the US, you don't have sediment even getting to the shelf. So the fact that this system is wide enough, it's on a trailing edge margin, so it has a fairly wide shelf surface, and the dynamic processes are able to steer it along shelf more than move it seaward.
Okay, so next, Gail.
Hi, that was really a great talk, and I learned a lot. Thank you.
Well, you were a co-author.
Well, I learned it when I read the paper, but
answer your own question now.
well, I guess my question is sort of the biggest, if we think back to where we were at the end of AMASEDS, I think one of the biggest differences is in terms of budget, and about, you mentioned a third of the sediment leaving Óbidos being trapped in the floodplain in the tidal river. And I guess do we need to rethink some of the other components of the budget on the shelf and the shoreline, or are we still pretty much where we were in terms of, it's just that input number that's leaving the river, or do we need to rethink what some of those estimates were in terms of, 15% being infected along shore and some small percentage in the plume, and the rest sort of going into the accumulation on the shore sets or the clinoform?
So in general, as science moves forward, there are always improvements, some of them driven by technology, some of them from understanding of other areas ideas can be imported. So in general, I would strongly encourage everyone that is interested in this type of system to try to get big studies going again. And to my Brazilian colleagues in particular, it would be great to get back out and to refine the understanding. What I presented is great, but I'm sure that all the pieces of the system, our understanding can be improved. I have had long discussions with Dave DeMaster about creating a figure that shows additional information. So that budget that I showed was one that we created at the end of AMASEDS. So that number of a third is a guess that's based on research that's decades old. There have been new numbers, especially some of the measurements that we've made in the tidal river. But I have trouble in general with the Amazon, and this is a personal issue, with the Amazon and all river systems, with the hanging too much emphasis on a single number for a river. Obviously, discharges and accumulations change over different timescales. They change, daily with tides. They change seasonally with big years and weak years, decades with environmental changes. What I tried to do, I put in the numbers in this presentation. I put in the numbers that scientists, including myself and colleagues, have generated. And those numbers are as good as those people were able to calculate, and they should have confidence limits wrapped around them. But what's more interesting to me, frankly, and I think more worthwhile, is understanding the processes that lead to those numbers. I think you can spend a lot of time focused on if it's a bigger number or a lower number. Just for example, the discharge past Óbidos. Each time I said that, I said Bob Mead's calculation of discharge. And as we know, there have been a lot of other people that have made estimates, and most of those are less than 1,200 million tons.
Okay.
I think that probably a really big, useful study would be to monitor at Óbidos as effectively as possible and come to some conclusions. There are all sorts of ways that you can make the numbers bigger or smaller, but I think that's the case for every one of the numbers that I showed. They're as best as the scientists could create, that created that number. They have confidence limits around them. And now they're changing because of environmental factors, the human impacts. My belief is we should focus on the processes that control the numbers and not get too hung up on exactly what the numbers are. Where the numbers are giving us orders of magnitude, I think that's the best we can do. As to where I would go to the whole system. Anyone who is interested and thinks any of the numbers or any of the processes are wrong, jump in there and prove that there's something, a better understanding of the processes and a better number you can come up with.
Okay, Shaka, you have to keep your answer as short as possible. Too many questions, sorry.
I just barely got started, Paul.
So we have a couple more. So Steve, your question is longer or short? If your question is short, I'll let you go first.
It's pretty short. So, and I apologize, I had another meeting at 10, so it was a short meeting, so I'm back. But while you were talking earlier, Chuck, you know, that figure that you showed from Summerfield with the transparent muds truncating the foresets in the northern part of the shelf area. So I've always been curious about that. And as you were talking, I wondered if that might have something to do with the development of Cabo Norte, because as you mentioned, Cabo Norte helps to focus the tides. And so has there been a progression over the Holocene where increases in tides as a function of the development of the Cabo Norte and the shore perpendicular shoal have changed is that the driving force behind the depositional change that's always been a mystery to me?
I don't know. I mean, as you know, all of us involved in the Amistad's days have had long discussions about what Cabo Norte is. Maracay Island is another very interesting feature, and the increased tidal ranges there apparently because there was accretion and now there's erosion of that shoreline. What causes that? Whether it's a change in marine processes, a change in fluvial processes, and we've gone through all sorts of scenarios. I don't know. I don't know what affects the history of Cabo Norte. I don't know what, and the shoal, and I don't know what caused the changes in that snippet of seismic profile that I showed. But I mean, it's what I was pointing out is that there are significant natural changes that occur. And I keep saying the word natural because I think that they're going to have to be superimposed before people jump to conclusions. There will be human impacts that make changes too, but before you jump to big conclusions about human impacts, we need to recognize the background, the baseline of natural variability in the system. And for that particular seismic profile, I mean, I could spend a lot of time now, but Paul doesn't want me to do that, giving all explanations. And so I'll conclude by saying, I don't know.
I mean, it'd be fun to test that idea that there's some sort of geomorphic evolution over time, and I'll leave it at that. So there's more questions.
But that just reiterates, it's time to go to the next generation. I mean, we're focusing out in the shelf. The big deal for me in since Amistad's days in the 90s was adding an understanding of the tidal river. I thought that was important. But now it's time to go back and refine our understanding of all these, and significantly because of this series. I mean, there have been lots of systems that are being described, most of them studied more recently than the 90s, and our understanding of those systems can probably create hypotheses, alternate hypotheses for what's happening in the Amazon. And I would strongly encourage people to go back to the Amazon and investigate the system with the past history in mind, our understanding in mind, but also some of these ideas from other systems.
That's great. So I think Peter already. Peter, are you still there? Can you unmute yourself? Pete Darling? Yeah, go ahead.
Sorry, Chuck, I had a question. The thing that haunts me is the discussion we had with Charlie, that you have this clinoform with its foreset with fluid mud layers coming off it. And they're pretty good fluid mud layers are going quite long distances on very low gradients. Are we sure they don't reach the canyon head? And then the foreset clinoforms, this prodigious area of muddy sediment accumulation in huge volumes. Are there landslides there? Does it fail?
So, I mean,
so are we sure it's closed there?
So that's a really, really interesting consideration. So decades ago, even before Amoseds, we had lots of interactions with Jim Coleman, whose perspective is one of the Mississippi system. And it's different because the rollover point there isn't in 40 meters, it's at sea level for the Mississippi. But as you know, on the foreset region of the Mississippi system, there are all manner of failures and erosive features that occur there. Maybe partly because it's shallower, so wave fluctuations have a bigger impact. But so Jim said that we were wrong. When we first went out in the 70s and did seismic profiling, we never saw evidence of landslide scars. And Jim said we were wrong. We were using the wrong techniques. And so we, in our cruise in '83, he didn't come out, he sent Charlie Adams out, and we spent a lot of ship time hours going back and forth along the clinoform, and never ever saw any evidence of significant relief, and certainly no evidence of failures and scarps that you often find on the foreset off of a delta. I don't know the reason. Now, as with Steve, I can give you some haywire ideas. My frank opinion is that the Mississippi is relatively quiescent through most of the year. You don't have much in the way of tides, even storms, except for the unusual hurricanes. It's a relatively quiescent environment, and that failures can be more significant because the fabric of the accumulating sediment is weaker. On the Amazon, the seabed is always being intensely reworked by the North Brazil current, by tidal currents, by wave resuspension, by the continuous trade wind activity. My feeling is that if a particle or particles are going to reside on the seabed, off the Amazon, in particular on the foreset, that they create a fabric that is stronger and more resistant to failure than off a system like the Mississippi. But the point is that there are fluid muds that are moving down. They're largely depositional and not erosional character, and they come to rest when you leave the gradient of the foreset, which is, is less than a degree, but when you come to the flat surface at the base, the bottom set.
Cool. And I saw Dave DeMoss and Marco Stick. Do you two have any question, comments?
I had a quick question about, do we have any quantitative estimates of the sediment discharge from the Amazon during glacial times? I know you're saying where the pathway is, but I'm wondering if we have any estimate. There are some places in the southern part of the basin that are more savanna-like instead of tropical rainforest. And I'm just wondering if there's any idea about the magnitude change between glacial and interglacial for the Amazon water and sediment discharge.
So Dave, I apologize. I'm not up on the data that's been created from the Amazon fan. There've been some recent drilling projects. I don't know what it is. I don't know how it compares to high stand conditions, warmer conditions, and the supply of sediment. There is no doubt, though, that there is a lot of sediment that has been reaching the distal part of the system during the glacial periods when the sea level is down and the sediment is delivering its load to the Amazon fan. There is lots of sediment that gets out there. How it quantitatively compares, I don't know. But I would encourage you or others to look at, Roger Flood, Jed Damuth, and the colleagues working with them. And then more recently, there was a drilling leg that was done out in the fan. And those may provide information at least about thicknesses of deposits and maybe from paleontological and maybe radioisotope dating. They may also say something about accumulation rates. I don't know how they reflect back to the basin.
Okay. So, Michael, do you have any questions?
Yeah, I mean, I was, with the discussion about the clinoforms, I was wondering about the clinoform slopes. I mean, the slide you showed, it looked like it was about a third of a degree. And I was wondering also if it varies along strike as you go, particularly, with grain size variations. Is it steeper in the sandier parts? And how does it vary?
Yeah, and as I said, it was less than a degree, and it does vary along slope. If you just look at that simple figure that I showed for bathymetry, you can see that. So the rollover point can be 30-ish, or we usually say 40, which is what I said here. And the base of the foreset, it can be in 60s, but we often say 60. But if you look at just the spatial difference between the 40 and the 60 meter isobath, you can see that it varies in distance. So the gradient also becomes steeper and more gentle along different parts. And I frankly, Steve, Dave, do you guys remember if there's a grain size correlation to the steepness of the slope? I'm not sure that we ever looked at that. And without letting those guys answer, part of the problem too is that when you're dealing with just muds, it was probably more difficult to resolve a clear difference. It isn't that some of it is coarse sand and others is mud. It's various degrees of silt and clay on the whole part of the system, with the exception, as Bob pointed out, right at the mouth of the river. And also, as Steve pointed out, there are some other places where we do see presence of sand that probably, like Cabo Norte, that is due to unknown factors. Steve, Dave, does anyone remember if there's a correlation?
I don't think we have the data to say about long foreset gradients and grain size. We haven't really looked at that. I don't think there's enough density in samples to do that.
I also want to make a comment. Actually, a couple of weeks ago, when I gave a talk on the SED online, the British sediment series, the same question asked me about the Yangtze or other Mekong to show any grain size trend change along shore transport. Basically, I don't remember we see any that kind of progress dating of the grain size decreasing. No. And the comments I want to make to the Amazon is, because as Chuck said, 90 or 85% of material sediment, mainly from the Andes, from 6,000 kilometers away from the river mouth. When those bunch of sediment travel all the way, the meandered from the floodplain, when they reach to the ocean, it's mainly, purely, very, very fine suspended load. So those very fine mud, basically, we didn't see any difference when they travel driving by the oceanographic current and settling down on the way. And also the stick, very fine stick, nature is make it very, very unlikely to have a sliding or slumping happen.
So an important, I don't think we're trying to sidestep the question of correlation, but one of the big issues is the fact that muds don't move as individual particles. They're flocks. Yeah. And so then you get into very deep have to do a deep dive into the correlation of discrete particle size with flock size. And maybe the question you're really asking is, do bigger flocks reside or reach the seabed on different parts of the foreset? And our measurements are of discrete sizes. Once you get into the bed, you can't come out and say what the flock was that took an individual particle there. There has been work, Kate Crank, Tim Milligan, Dick and students have done work with flocks in the water column. But again, that doesn't take you to the bed. Once you get to the bed, it's hard to say what size flock the individual particles arrive with or within.
Okay, I think, it's almost 2 hours for Chuck, you sitting here. And I thank you very much for this fantastic talk. And I think the whole community will benefit about your effort. And I know you get up at 3 a.m. this morning and, so you're still in your office. I guess you must be very hungry. And so thank you very much. And maybe you need to get up to go to the bathroom. And I need to rush to bathroom.
I thought he was just getting started.
Yeah, I'm going for my first Bloody Mary.
Okay, next Wednesday, we have Shuya talk about the Yangtze. So please do come back. So otherwise than that, so this talk is also, as always, we recorded archive on the YouTube. And Chuck will also share the PDF of his talk, the presentation. So if anybody need any detailed information, you can directly write an email to Chuck. And but otherwise than that, I think we have to stop here. Many people have other meetings at 10:30. So thank you very much, Chuck. Again, thank you.